All right, everybody, welcome back. I am so excited for today's deep dive because we are tackling a real head-scratcher, the Collatz conjecture.
Ooh, yeah. This one's a classic.
It is, and it's been stumping mathematicians for ages. You start with any number, right?
What? Any whole number?
And then you apply this simple rule. If it's
Yeah.
even, you divide it by 2. If it's odd, multiply by 3 and add 1. You just keep repeating that.
And the big question is, does it always eventually go down to 1?
Always down to 1. That's the million-dollar question. That's the conjecture. Now, you know our wonderful listeners, they have done some digging and sent us some really interesting research on a new way to look at this, a new framework called CMSN.
Collatz-Matthews Sequence Networks.
Catchy, right? So maybe, just maybe, the CMSN could help us unravel this mathematical mystery. I'm excited to dive in. Are you ready?
Absolutely.
Awesome. So let's start with the basics. What exactly is this CMSN? What makes it different from how we usually think about the Collatz conjecture?
Well, the cool thing about CMSN is it doesn't just focus on whether or not a number reaches 1. It's kind of like, instead of just checking if you finish a race, it's looking at how you ran it, you know?
Okay, I like that analogy. So instead of the finish line, what are we looking at?
We're analyzing the whole journey the number takes using 4 different, what we call metrics.
4 metrics. All right, lay them on me.
The first one, that's called backracks. It's just the total number of steps it takes to get down to 1. The classic way to think about it.
Right, so if it takes, let's say, 5 steps, backracks is 5.
Exactly. Then there's by, and this one's a bit more, this one's where we get a little more technical. It's the sum of the logarithms, base 2 of all the odd numbers in the sequence.
Hold on. Logarithms. Are we in high school math class again? Why are we bringing logarithms into the picture?
Think of it this way. By is kind of like a measure of how much those odd numbers are trying to make the number bigger, like their growth potential. It tells us how much they're pushing upwards.
Okay. So it's not just about how many steps, but how much those odd steps are really inflating the number, right?
Right. And then we have BZ. That's just a simple count of how many odd steps there are.
Okay, keeps it nice and straightforward.
Bar.
Even steps versus odd steps. Got it.
And last but not least, we've got G. This one is a little more nuanced, but basically it's a more precise measure of how much those odd steps contribute to the growth of the number.
So we're really dissecting the role of those odd steps. We've got the total steps, BX, the odd step growth potential, by, the number of them, BZ, and then their actual growth impact, G. Okay, I think I'm following so far. But why are these metrics so important? What makes them special for the Collatz conjecture?
The key is that by analyzing these metrics, especially how they relate to each other, we get brand new insights into how the Collatz process actually works. It's like before we were just looking at the problem with like one eye closed.
Okay, so CMSN gives us a much wider perspective. I'm really curious to hear what the researchers were able to find using this new framework.
Well, they analyzed a whopping 30 million sequences, and what really jumped out was this ratio of B's to B's. Remember, that's the proportion of odd steps to the total number of steps.
Yeah. So like if a sequence took 10 steps and 5 were odd, that ratio would be 0.5, right?
Exactly. And what they found is that across those millions of sequences, that ratio consistently stayed below 0.388.
Wow. That's incredibly consistent across that many sequences. Does that hold true even for sequences that take a really long time to reach 1?
Yeah. Even sequences that took over 700 steps, they still followed that pattern. It really seems like there's some underlying structure there hidden within this, seemingly random process.
That's wild. So does this mean we're on the verge of finally proving the Collatz conjecture?
Not quite. It's tempting to think so, but we got to be careful. That 0.388 ratio, it's a huge clue, don't get me wrong, but it's based on a limited data set. We haven't tested every single number.
Right. So we've got this tantalizing piece of the puzzle, but we're not at the finish line just yet. What's the missing piece? What would take us from a strong hunch to an actual rock-solid proof?
We've got to prove that this observed pattern, especially that crucial BZBX ratio, holds true for absolutely every number, not just the ones we've tested.
I see. So how do we get there? How do we go from observation to a guaranteed full-blown proof?
Well, the researchers have a pretty ambitious proposal. Analyze a monstrous data set, 10 billion sequences.
10 billion. Wow. That's a computational challenge, to say the least. What are we hoping to find by going that big?
We're looking for confirmation. If that 0.388 bound holds firm across such a massive data set, it would give us immense confidence that the conjecture's true.
So we need some serious computational firepower to potentially crack this code. What else, besides just brute force number crunching, can we do?
Well, the researchers also point to some really fascinating theoretical
Oh,
avenues.
interesting. What kind of theoretical approaches are we talking about?
It's like having a two-pronged attack, computation on one side, theory on the other, both trying to break through the Collatz mystery.
Yeah, I'm really liking this two-pronged attack analogy.
Yeah.
But before we get too far down that theoretical path, I want to go back to something you mentioned earlier, those other interesting findings from the CMSN
Oh,
research.
yeah, yeah. We got so caught up in that BZ-BX ratio, there's more to uncover. Remember those four CMSN metrics? BX, BI, B, Z, and G. They give us so much more information than just whether a number gets to 1 or not.
Right, right. It's like we're not just watching the finish line, we're analyzing every twist and turn along the way.
Exactly. And when the researchers looked closely at those metrics, they found another fascinating connection, this relationship. It's BXBZG. In other words, the total reduction you get from all the even steps, it always ends up being bigger than the growth from the odd
Wait,
steps.
so you're saying those drops, those divisions by 2, they always overpower the jumps upwards, even when you're multiplying by 3 and adding 1?
That seems to be the case, yeah. And it gives us a really compelling reason why these sequences might always head towards 1.
It's like there's this built-in bias towards shrinking the numbers, pulling them back down no matter how much they try to jump up. I'm starting to get why mathematicians are so hooked on this.
It really is a tempting clue, a hint at some underlying mechanism. But again, just like with that BZBX ratio, we got to remember this is based on what we've seen, what we've observed. We still need that solid mathematical proof to be absolutely sure.
Right, right. No jumping to conclusions just yet. But still, it makes you wonder, is there some elegant mathematical explanation hiding behind all of this? Some underlying principle that governs this seemingly chaotic process?
That's the big question, isn't it? And that's where those theoretical approaches come in. The researchers suggest exploring connections between CMSN and other areas of math, like dynamical systems and ergodic theory.
Okay, gotta admit, those sound a little intimidating. Can you break it down for me? What does those fields have to do with the Collatz conjecture?
Well, think of a dynamical system like any process that changes over time based on some rules, like the weather, the stock market, or how many rabbits are in a field. Those are all dynamical systems.
So basically, anything that evolves over time following certain rules.
Exactly. And the Collatz process, with its simple rule, divide by 2 if even, multiply by 3, and add 1 if odd, that's a dynamical system too. We're watching how these numbers change over time according to this rule.
Okay, that makes sense. But what about ergodic theory? What's that all about?
Ergodic theory, it's all about the long-term behavior of these systems. It asks questions like, do they eventually settle into some predictable pattern, or do they stay chaotic and unpredictable forever?
So are we asking if those numbers, after all that jumping up and down, eventually fall into a predictable pattern converging to 1?
You got it. And the fact that CMSN revealed these consistent patterns, these ratio and relationships, it suggests there might be some underlying order, some ergodic behavior controlling the whole thing.
Wow, that would be huge. It would mean the Collatz conjecture, instead of just being this mathematical curiosity, might be showing us something much deeper, some fundamental mathematical principle.
That's a pretty exciting thought, right? And there's another part of the CMSN research that could give us even more clues, the outliers.
Oh yeah, you mentioned them before, the sequences that take an unusually long time to reach one, or the ones that hit super high numbers along the way.
Exactly, those outliers. They could help us understand the limits of these patterns we've seen, the points where the Collatz process might get, a little wild, like stress tests, pushing our understanding to the limit.
So by looking at those rule breakers, we might get a better sense of when and how the Collatz process really gets crazy, maybe even reveal some weaknesses in those patterns we've been talking about.
Right. They might help us refine our models, figure out critical thresholds, and hopefully get us closer to a real proof.
Every new discovery seems to add another layer to this already fascinating puzzle. So where do we go from here? What's the next step in this investigation?
Well, on the computational side, we've got that massive analysis of 10 billion sequences. If we can get the computing power, that could give us a ton of new information.
Imagine being the one to find that one sequence buried in those 10 billion. That breaks the pattern. It would turn our whole understanding of the Collatz conjecture upside down.
That's the beauty of scientific exploration. You never know what you might find. But even as we're waiting for those computational results, there's lots of exciting work going on in the theoretical side of things, too.
Like connecting those CMSN metrics to ideas from dynamical systems and ergodic theory.
Exactly. And There's one more interesting thing to consider, the possibility of a heuristic proof.
Okay, you mentioned that term before, heuristic proof. It's not a formal mathematical proof, though, right?
Right. A heuristic proof is more like a really strong argument based on the patterns we've seen in logical reasoning. It doesn't have the absolute certainty of a formal proof, but it can still be very convincing and guide further research.
So for the Collatz conjecture in CMSN, what would a heuristic proof look like?
Well, remember, that key observation, the reduction from the even steps is always bigger than the growth from the odd steps. That relationship, Bx, Bzg, along with that consistent Bz-Bx ratio below 0.388, that forms the foundation for a possible heuristic argument.
So if we can show that those two observations hold true for a huge number of sequences, we can make a pretty strong case that the Collatz conjecture is probably true, even without a formal proof.
That's the general idea. It wouldn't be the final answer, but it would be a big step forward in solving this age-old mystery.
This is all incredibly thought-provoking. We started with a simple rule about even and odd numbers, and now we're talking about these deep and complex areas of math. It's amazing.
It really is. And you know, this deep dive has got me thinking. The researchers who developed CMSN, they didn't just find these patterns, they created a whole new way of looking at the problem.
That's a great point. Sometimes all it takes to make progress on a problem that's been stumping people for decades is a fresh perspective, a new set of tools.
Exactly. And it makes you wonder what other seemingly impossible problems could be solved with a little ingenuity and a new lens to look through.
I love that, and I think that's a perfect place to take a breath and let all this sink in for a minute. It's been a whirlwind tour through the world of the Collatz conjecture, and I think I need a moment to process all these awesome insights. All right, we're back and ready to wrap up our Collatz conjecture deep dive. I'm still blown away by how a simple math puzzle can lead to such complex mathematical ideas. It just shows how connected everything is, doesn't it?
Totally. The CMSN research is like a perfect example of how different areas of math can come together in these surprising and really interesting ways.
Before we finish up, I wanted to go back to that experiment we talked about, the one where they want to analyze 10 billion sequences. Imagine if we had all the computing power we needed right here, right now. What would be the next step in our investigation?
Well, we'd fire up those supercomputers, let them loose on those 10 billion sequences. Each sequence could have tons of steps, and we'd be glued to the screens, watching to see if that BZ-BX ratio, the proportion of odd steps, stays under 0.388.
So we're basically looking to see if the pattern holds up, right? Even more confirmation. But what if we found a sequence somewhere in all those numbers that breaks the rule? What if that ratio goes above 0.388?
Now that would be a wild discovery. It wouldn't automatically mean the conjecture is wrong, but it would definitely challenge what we think we know. We'd have to dig deeper, figure out what makes that sequence so special, and see if it points to some deeper pattern we haven't found yet.
Like finding a hidden clue that changes how we understand everything. It could open up a whole new path of research. So no matter what, whether that 10 billion sequence experiment proves us right or throws us a curveball, it's a win for mathematicians.
Absolutely. It just shows how powerful exploration is in math. Both empirical exploration, like with all those computations, and theoretical exploration, delving into the deeper math behind it all.
And speaking of theoretical exploration, we talked about those connections to dynamical systems and ergodic theory. Where do you think those connections will lead? Could they help us find that formal proof everyone's looking for?
It's definitely possible. If we can really show that the Collatz process as a dynamical system has this specific ergodic behavior that always leads to one, that would be a major step towards a proof. It would give us the theoretical foundation for all those empirical observations we've been discussing.
So it sounds like we're just at the start of a really exciting chapter in the Collatz conjecture story.
For sure. This CMSN framework has given us a whole new way to look at this problem, and I bet mathematicians will keep pushing the boundaries with large-scale computations, theoretical breakthroughs, or maybe even both.
And maybe, just maybe, one of our listeners will be inspired by this deep dive and make their own contribution to solving this mathematical mystery. Who knows? The next big breakthrough could come from someone listening right now.
That would be awesome. The Collatz conjecture has a way of catching people's attention. It's simple enough for anyone to understand, but it's also deep enough to challenge even the brightest mathematicians.
We've definitely covered a lot today, from the basics of the Collatz conjecture to all the details of the CMSN framework and what it might mean. It's been a real mental workout, in a good way.
It's been fun exploring all these cool ideas with you. And you know what? Even after all this, I still find myself amazed by how simple and elegant that Collatz rule is. Even, divide by 2, odd, multiply by 3, and add 1.
Mhm.
So simple, yet it creates so much complexity and mystery.
It reminds us that sometimes the most profound mathematical truths are right there in front of us, just waiting to be discovered.
And sometimes all it takes is a fresh perspective, some new tools, and a lot of curiosity to unlock those hidden truths.
Couldn't have put it better myself. So to all our listeners out there, keep that Collatz curiosity burning. Explore, experiment, and who knows, maybe you'll be the one to finally solve it. Until next time, keep on diving deep.